Today we are going to cover the concepts of complex power and, if we have time, power factor correction. So complex power is a quantity that's used by power engineers to kind of succinctly characterize the power that's absorbed by a given load in a steady state sinusoidal system. The complex power as a quantity actually contains a lot of different pieces of information, which is why it's so useful. Okay? Our complex power relationships are going to involve working or analyzing circuits in what I like to call the RMS phasor domain. So before we fully begin talking about complex power, I want to introduce the RMS phasor domain so that you all understand where we're going. So let's say that we have a steady state sinusoidal voltage V of t that can be expressed as Vm cosine omega t plus some phase angle V, or a steady state sinusoidal current I of t that could be expressed as Im cosine omega t plus theta I. As we should already know, these are the time domain representations of these signals, and we have learned to convert these signals into the frequency domain by using phasors. So the frequency domain representation of our time varying voltage signal would be V with a bar over it. It is equal to Vm angle theta V. We simply keep the magnitude and phase angle of our sinusoidal signal. And similarly, our phasor current would be I is equal to Im angle theta I. We can take this frequency domain representation one step further to get into the RMS phasor domain. Okay. So an RMS phasor voltage will be V with a tilde over it. Okay. That's the symbol that I use. And this is simply our phasor voltage V divided by a factor of the square root of 2, because the effective or RMS value of a steady state sinusoidal signal is simply the magnitude of that signal divided by the square root of 2. So this is going to look like Vm over root 2 with an angle of theta V, or VRMS with an angle of theta V. And we can do the exact same thing for our current relationship. So our RMS phasor current I with a tilde over it is just our phasor current I divided by the square root of 2, which looks like Im over the square root of 2 angle theta I, or IRMS angle theta I. And we call this the RMS phasor domain. So one great thing about the RMS phasor domain is that it has the exact same impedance relationships as the frequency domain that we've been working in for the last several class meetings. So really the only thing we need to look for is whether or not our voltage signal is expressed in terms of volts, in which case we know it's in the frequency domain, and we need to convert it to the RMS phasor domain by dividing the magnitude by the square root of 2. And if the voltage is given with units of volts RMS, we're already in the RMS phasor domain, and we can just use all of the regular steady state sinusoidal techniques that we've developed over these last several class meetings. All right, so now we can get into the actual complex power relationships here. So for a generic impedance Z, like so, that has a RMS phasor voltage drop across it and an RMS phasor current flowing through it, the complex power is defined to be S is equal to the RMS phasor voltage times the complex conjugate of the RMS phasor current. The units of complex power are the volt ampere. So I want to talk about this unit here very briefly, okay? A volt ampere is, I hope pretty obviously, simply 1 volt times 1 ampere. We are more familiar with that combination being used to describe watts, the unit of power that we've dealt with to this point. Because complex power is a combination of different types of power, we use different units to describe the different portions of the complex power, okay? So when we're describing the complex power itself, we have units of volt amperes, okay? Dimensionally the same as a watt, but if you hear about something being expressed in terms of volt amperes, you know that we're dealing with a complex power relationship. All right, so since the complex power is the product of a RMS phasor voltage and an RMS phasor current, these are just complex numbers. And so that means that we will have a polar form representation of our complex power and a rectangular form representation of our complex power. So let's start with our rectangular form representation, okay? So here I'm going to state simply that V RMS phasor is V RMS angle theta V, and our RMS phasor current is I RMS angle theta I. And now we're going to do the indicated multiplication, okay? So our complex power S is the product of our voltage, so VRMS angle theta V, times the complex conjugate of our current. The complex conjugate means that we need to change the sign on the angle, so that's going to be minus theta I. And what this gives us is VRMS times IRMS cosine theta V minus theta I plus J VRMS IRMS sine theta V minus theta I in rectangular form. Each of these parts has a special name. So this bit right here, VRMS IRMS cosine theta V minus theta I, is what we call the average power, and it is measured in watts. As I showed you at the end of our last lecture, this representation is the exact same average power that we were dealing with using just our instantaneous power and average power relationships that we developed when we began our discussion. This RMS phasor domain representation is absolutely equivalent to what we dealt with earlier. Okay. So the average power is the real part of the complex power. And what it represents is the portion of the complex power that is capable of performing work on a load. Okay. That work is usually defined as converting electrical energy into heat, but there are some alternative definitions as well. That's the one that we'll stick with because that's the one that's most closely aligned with the circuit theory that we've dealt with to this point. Over on the right-hand side here, the quantity VRMS, IRMS, sine theta V minus theta I is known as the reactive power, Q. And the units of reactive power are volt amperes reactive. I'm going to put a note out here. Reactive power. This is simply the imaginary portion of our complex power, S. And effectively what reactive power represents is energy storage in our system. Okay, we will not have a reactive power component of our complex power unless there are capacitors and or inductors in our system. So reactive power does not represent power that can be used to perform work. And the reason why I say that is because reactive power represents the power absorbed or supplied by energy storage elements. If we looked at the instantaneous power absorbed by a capacitor or inductor, and we did this a couple of days ago, the average power, or the real part of that power, was 0. So exactly half of the time, energy or power is delivered to an energy storage element in a steady state sinusoidal system, and exactly half of the time that energy storage element is giving that energy back to the source. Now, you may ask yourself, well, if reactive power just represents power being transferred back and forth between the source and a load in a system, what does it actually do? So reactive power is used in electricity distribution as a form of temporary energy storage. Without a reactive power component, we would see significantly more blackouts and power outages than we do, because the load that's seen by the electrical grid is constantly changing, and the reactive power is what helps bring things up when the load is slightly exceeding what our current demand is. It gives us time to fix things, okay? So consider a classic example is what happened in Great Britain several years back, where it was after, I believe, a World Cup match. Everybody turned on their electric tea kettles at the same time after the match was over, and it actually caused a brownout throughout London. And it was because they didn't have sufficient reactive power stores to ride out that large increase in demand at that instant, okay? So reactive power is used largely to stabilize the grid. It's also used to keep rotating electric machinery running at maximum efficiency. Okay? In a rotating electric machine, the reactive power is what maintains the magnetic flux, which keeps the rotation constant. Electric induction motors are actually the largest consumers of reactive power in the world. All right, so we can express our complex power also in terms of a polar complex number, right? That polar complex number representation would be V RMS, I RMS, angle, theta V minus theta I. Well, the quantity VRMS times IRMS is more commonly known as the apparent power, which I will define as the magnitude of the complex power. So it has units of volt amperes as well, and it simply represents exactly the magnitude of the complex power. So complex power without any phase angle contribution. So because the apparent power is the complex power without any phase angle contributions, in a sense, it represents the worst case scenario because it's the product of effectively the peak value or the effective value of the voltage times the effective value of the current that isn't reduced by any phase angle difference that may be present. Okay, so the quantity of apparent power is what most electrical systems are designed towards. The apparent power is used to determine what size of conductors are needed for specific projects based on the RMS current draw, things like that. If you've ever purchased a uninterruptible power supply or anything like that, you may see that it's rated for some number of volt amperes and then some lower number of watts. Effectively, that's telling you both the apparent power rating and the average power rating, letting you know effectively that you can put so much real load and only probably a smaller portion of reactive load into that system to have it operate correctly. I'm running out of space here, but we have this bit as well, the angle. Which we'll more commonly call theta S, or the power factor angle. So one very important thing to note regarding the power factor angle is that by definition, it is equal to theta V minus theta I, which is the exact same thing as the angle of the impedance that we're determining the power over, okay? So the power factor angle can actually be used to tell us a lot of information about the characteristics of the load that we're measuring the complex power over. And we'll get into that in just a few moments. Okay. So this brings us to our next topic, and this is really kind of a subtopic within complex power. And that is the concept power factor. So the power factor at which an electrical element or network operates at is a measure of the efficiency of power transmission to or from the network. Mathematically, power factor is defined as the ratio of the average power to the apparent power, which is simply cosine theta v minus theta I, or cosine theta s. All of these relationships represent the exact same thing, okay? So, as I said a few moments ago, the power factor is a measure of efficiency of transmission. So in an ideal case, a power factor would be 1, which means all of the complex power that's delivered to a load is composed of average power. And so all of the power that's being transmitted is capable of performing work. The worst case scenario is when a power factor is 0. Power factor is 0 when we have a purely reactive load and effectively none of the complex power that is being delivered to the load is being used to perform any work. All of it is getting sent back and forth between the source and the load. Because the power factor is dependent on a cosine relationship, that means that the power factor values range from -1, where the network is supplying apparent power at 100% efficiency, to +1, where our network in question is absorbing apparent power at 100% efficiency. When a load is operating at a power factor less than a magnitude of 1, it means the source is being required to generate more than the minimum amount of volt amperes necessary to supply the required average power needs of the load. This typically means that the expense to the supplier, the person who's generating the power, is higher than the cost to the customer, as more energy needs to be generated, which requires a more expensive infrastructure to supply the currents, okay? We're going to talk about that concept significantly more a little later on when we talk about the concept of power factor correction, okay? But before we get there, I want us to learn a little bit more about power factor, all right? So, power factors can be classified as either leading or lagging. What this leading or lagging means is the relationship of the phase angle of the current with respect to the phase angle of the voltage, okay? So if our power factor angle is between 0 and positive 180 degrees, we consider our system to be operating at a lagging power factor. If negative 180 degrees is less than our power factor angle, is less than 0 degrees, then our system is operating at a leading power factor, okay? Now, there are a few special cases that we need to talk about as well. If our power factor is equal to 1, either +1 or -1, we typically call this unity power factor. And unity power factor is neither leading or lagging. This typically corresponds to theta S is equal to 0 or theta S is equal to plus or minus 180 degrees. If our power factor is 0, we also have a situation that is neither leading nor lagging. And this occurs when theta S is equal to plus or minus 90 degrees. Typically speaking, loads that operate below a specific power factor threshold, usually set by the electric utility, incur fines from the utility company supplying the power to offset the increase in transmission costs. These fines can be avoided by applying power factor correction techniques, which I mentioned earlier, and we're going to talk about a little bit later. But before we do that, I want to introduce what I believe is a handy visual tool to help us understand the relationships. And I think that this is necessary because I just want to go over all of the different equations that I've introduced today. So we have this guy right here for our complex power. We have this guy right here for our average power. This guy right here for our reactive power. This guy right here for our apparent power. This guy right here for our power factor angle. And then this combination of relationships right here for determining power factor. That's a lot of equations to hit you guys with on a single day. So what we're going to talk about now is the power triangle, which relates all these quantities. So for a generic load, Z, expressed in rectangular form, but it actually doesn't particularly matter, R plus JX, where R and X are positive, complex power absorbed by Z can be represented graphically as this. So effectively, I'm just going to make a simple complex plot that represents our complex power. So our vertical axis here represents the imaginary portion of the complex power. Our horizontal axis here represents the real portion of our complex power. And let's say, just for the sake of argument, that our complex power S, something like this. The projection of our complex power onto the real axis is simply our average power. The projection of our complex power onto the imaginary axis is simply our reactive power. The length of this 2D vector is the apparent power, and the angle formed with the real axis is the power factor angle. So our complex power S, which is by definition the product of our RMS phasor voltage times the complex conjugate of our RMS phasor current, can be expressed as P average plus JQ, or so effectively real power plus, or excuse me, apparent power, gosh, I'm getting this backwards, average power plus J reactive power. And then in our polar form representation, we have apparent power angle, power factor angle, okay? All of this information is buried inside this power triangle. And it's interesting here that all of this information is actually just buried inside of your calculator's ability to convert back and forth between polar form and rectangular forms for complex numbers. So effectively, if you can carry out this mathematical operation and you understand that the real part of the result is the average power, the imaginary part of the result is the reactive power, the magnitude of the result is the apparent power, and the phase angle of the result is the power factor angle, you don't actually have to memorize any of the equations that I developed a few minutes ago. Everything is buried inside this simple relationship and this simple picture, okay? The value of theta S tells us a lot about what type of load we have. Okay. So if theta S is equal to 0, our power factor is 1, and our impedance Z must be purely resistive, meaning R is greater than 0 and X, the reactance, is equal to 0. If, excuse me, theta S lies between 0 and 90 degrees, our power factor is lagging, and Z is considered inductive, where R is greater than 0 and X is greater than 0. If theta S is exactly equal to positive 90 degrees, our power factor is 0, and our load Z is purely inductive, R is equal to 0, X is greater than 0. If our power factor angle lies between negative 90 degrees and 0 degrees, our power factor is leading and Z is capacitive, meaning R is greater than 0 and X is less than 0. And finally, if theta S is equal to negative 90 degrees, our power factor is 0 and Z is purely capacitive. R is equal to 0 and X is less than 0. Now, technically, I've left off half of the unit circle that corresponds to negative resistances. The only time we would ever see anything like that, or a power triangle that would ever lie not in quadrant 1 or quadrant 4, which is what I've defined here through all of these relationships, would be if we were looking at the complex power absorbed by a load, or excuse me, absorbed by a source, which typically speaking we wouldn't do. We would look at the complex power supplied by a source, which should land us in quadrants 1 and 4, and all of these relationships would be valid. All right. So what I want to introduce now are alternative relationships for complex power. So effectively, variations on this product that will allow us to only know the RMS phasor voltage across our element or network of interest, or the RMS phasor current flowing through our element or network of interest. So it should not be much of a surprise that Ohm's law in the RMS phasor domain is the same effectively as Ohm's law in the frequency domain. So we could say that Ohm's law is simply RMS phasor voltage V is equal to RMS phasor current I times impedance Z. I can say this is true without any real derivation or anything, because we know inherently that, write it down, phasor voltage V is equal to phasor current I times impedance Z, because we went through a full derivation for that. And if I divide both sides by the square root of 2, I'm getting my RMS phasor relationship. So Ohm's law has to work out here. So what we can do is we can use that relationship to manipulate things. So what I mean by that specifically is, by definition, our complex power S is V times I conjugate. Well, if we replace V with I times Z, what we have is I times Z multiplied by I conjugate, which is I conjugate times I times Z. Do any of you guys on Zoom know what I conjugate times I should give us? All right, well, let's see. I'm going to do this as an aside here at the bottom just to show you what's up, and then I'm going to wind up erasing it. But if we have a complex number A, where we have the magnitude of A with a phase angle of theta A, then a conjugate would be the magnitude of A with an angle of negative theta A. So A conjugate times A would be magnitude of A angle negative theta A multiplied by the magnitude of A angle positive theta A, which comes out to be just the magnitude of A squared. So anytime we have a complex number multiplied by its conjugate, we just get the square of the magnitude. Okay. So the magnitude of our RMS phasor current is just the effective value. So this is just going to be I RMS squared times Z. So if we know the impedance, we only need to know the magnitude of the current flowing through it in order to determine our complex power. Similarly, we could start with V times I conjugate, and we can express I conjugate as, so let's see, we're going to have V here. So I is V over Z. And we're going to conjugate this fraction. Well, when we conjugate a fraction, we have the conjugate of the numerator over the conjugate of the denominator. So this is going to look like V conjugate times V over Z conjugate, or VRMS squared divided by Z conjugate. So effectively, we only need to know the impedance value and the magnitude of the voltage drop across the impedance in order to determine the complex power. Now, let's take this one step further and develop relationships specifically for resistors, inductors, and capacitors. Okay. For resistors, where R is greater than 0 and the reactance is equal to 0, what we will find is that SR, the complex power absorbed by a resistor, is simply I RMS squared times R, or VRMS squared over R, which means resistors absorb average power. That's their purpose in a steady state sinusoidal network. for inductors, where R is equal to 0 and X, the reactance, is greater than 0, we'll have SL, the complex power absorbed by an inductor, is J omega L times I RMS squared, or J times the RMS squared over omega L, which means inductors absorb reactive power. And finally, for capacitors, where R is equal to 0 and X is less than 0, we have SC is equal to negative J times I RMS squared over omega C. And this is equal to negative J omega C times VRMS squared, which tells us that capacitors supply reactive power. Now we're ready to talk about the concept of power factor correction. So large industrial consumers, like manufacturing plants, often operate at a power factor of less than 1 due to the presence of numerous inductive loads like electric motors. To avoid being fined by their distribution utility, a technique known as power factor correction can be employed to raise their operating power factor to an acceptable level. So let's consider a power triangle diagram for a generic inductive load. So here's our imaginary axis. Here is our real axis. And let's say that this complex power, we're going to call it S old. It represents the complex power absorbed by the network prior to power factor correction. Projection of S old onto the real axis we'll call P old, representing the average power absorbed by the load prior to power factor correction. And the projection of S old onto the imaginary axis will be Q old, the reactive power absorbed by the load prior to power factor correction. And this angle right here we'll call theta old, which is the power factor angle prior to power factor correction being applied. Okay. So the goal of power factor correction is to increase the power factor at which the load operates. So what that means, and just as a quick reminder here, power factor is defined as average power divided by apparent power, or cosine of the power factor angle. So if we want to increase our power factor, we need to make theta, or theta s, our power factor angle, smaller. How we are going to accomplish this is by placing a capacitor in parallel with our network. Now, recall from just a few moments ago that a capacitor's job is to supply reactive power to a system. So effectively, if we have a capacitor supplying some amount of reactive power, so the direction on this is straight down, indicating we are absorbing negative reactive power or supplying positive reactive power, then our corrected power factor, excuse me, our corrected complex power would look something like this. Our projection onto the real axis is still P old. Our projection onto the imaginary axis will be Q nu. Let me write that more legibly. And the angle formed, been doing the angles in orange, will be theta nu. Okay. So this is how the process of power factor correction works. We put a capacitor in parallel with our load, which injects VARs into our system, offsetting the amount of VARs that are being absorbed by our inductive load, yielding a complex power that operates at the same amount of average power absorption, but a lower amount of reactive power absorption, which in turn implies that our power factor has been increased. Okay, so now let's throw in some actual math. Okay. S old, our complex power absorbed by our load prior to power factor correction, is simply P old plus J Q old and S nu, our complex power after power factor correction, is simply P old plus JQ nu. The amount of complex power that is absorbed by our capacitor is simply the difference of S nu and S old. So we'll have S nu minus S old, or P old plus JQ nu minus P old plus JQ old. gives us J Q new minus Q old. I want to make a note here. This will always be a negative quantity. The reason why it will always be a negative quantity is because we are doing everything here in terms of absorbed power, and our capacitor supplies reactive power into our system. Okay. We can call this combination of Q new minus Q old Q cap, which is simply the reactive power absorbed by our capacitor. Okay. So how we relate this to a capacitor value, I'm going to scroll back here one page, is by using this relationship, because we have now this relationship tells us the complex power that is absorbed by a capacitor, and this relationship also tells us the complex power absorbed by a capacitor. So if we equate those two relationships for complex power absorbed by a capacitor, what we will get is that the capacitor value C used for power factor correction will come out to be negative Q cap. So negative times this negative quantity is going to give us a positive capacitor value, divided by omega, our frequency of system operation, multiplied by VRMS squared, where VRMS represents the magnitude of the voltage drop across the capacitor. Okay. That's one relationship. I would argue that it's a tedious relationship to use because we have to do a reasonable amount of work to get those quantities. A slightly better representation, in my opinion, is this one. P old multiplied by the tangent of theta old minus the tangent of theta new, divided by omega VRMS squared. I prefer this relationship because typically speaking, we'll be given an old power factor that's related directly to theta old and a new power factor that's related directly to theta new. So the information that we need in order to employ this equation is fairly straightforward to find. Okay. All right, so that's all I'm going to talk about for today. I understand wholeheartedly that I introduced a ludicrous amount of equations today, and we have not yet applied literally any of them. So our class meeting on Friday will be dedicated entirely to working problems utilizing these relationships to help you understand how they're used. If, while I'm working on an example problem, anything seems confusing, questionable, or however you want to put it, if it just seems off to you and you don't understand why I'm doing it or where it came from, please stop me and we'll talk about it. All right, unless anybody has any questions for today's stuff, I am done talking and I will see you on Friday.